Hi everyone, and welcome back to week 2 for now. And in this week we're going to talk a lot about fragmentation. So for creating dynamic, for creating distraction for our ship, we need to pass a few stages. So the first stage is creating the frags. So fragmentation is basically the first thing we need to work with. We already prepared geometry. So we have our ship in a proper position. We have the thickness. We have a geometry. So we now should create fragments. But before we go into the dynamic, the second thing we should create, and we will do this a little bit later in this week, is creating the constraints. Let's call this like this. Sorry, I tried to type with a mouse, so it's a little bit bad. Okay, so the constraints is very important also because we need to keep our fragments together, because if we just make fragments and put the ship on the water, it just separate into individual pieces and just fall down. So we need to keep all those fragments together. Also, constraints can create different functions. In our case, we will use a constraint for create some kind of deforming for the metal. The third one is basically our dynamic. So we will create distraction. That's we will do for now in week 2. In week 3, we will use a dynamic simulation, so basically distraction using those fragments and constraints we create today. And the 4 is working with the cache. And you can say, okay, the cache mainly used for rendering, but in distraction, well, in many cases, even with volumetric simulations, we can take a cache and make something. In our case, we will use our dynamic simulation to drive the cache. Okay, or use this cache to drive our fragments, to make a bending, to make deforming and all this thing, and prepare this cache for rendering. And this cache will go also into different stations like a volumetric simulation, the water simulation. We will convert this into VDB and etc. So the first 2 stages we're going to cover in this week, and the second 2 stages we're going to cover in the next week. So now about fragmentation. Let me just a little intro, because I hope that many of you already know how fragmentation works in Houdini and the main methods we can use for fragmentation. But to make sure that you won't have too many questions on that, I will just show you a quick example, the main ways how we can create fragmentation in Houdini, just very quickly. So let's select the geometry, create geometry. In fact, I want to hide other objects, or actually I want to turn off the visibility of our ship because there's a lot of objects. I don't want to look at that. So let's call this frags test. And create, I don't know, what a test geometry we have here. The Greg, I don't know, maybe it's not the best. Maybe you, the rubber toy. We will fragment you. Go to this guy and let's make fragments based on this stuff. So I think you know that there is 2 main methods of creating fragments in Houdini. Well, in many softwares too, is using the Boolean and using the Voronoi. So let's create a Boolean. What Boolean means? Well, in many cases, Boolean used for intersecting, for union objects and other stuff, but in our case, we will cut one object with another one. So if I want to slice this guy, if I go here and use an exploded view, let's connect it here. You can see that we already have some elements because we have a separate names for this element. We have shop material and the different type of toy shader and all other stuff, so we can separate this object into a parts. But if I want to cut this geometry into the pieces, I can take a grid, okay, something like that, and I don't know, maybe rotate it, not like this, like this. Go to Boolean And if you have a Boolean structure, we'll talk a little bit about this too. And except of the intersection, I want to set the shutter. So the shutter is now using the pieces of A. So we have the AP input and B input. So I turn off this grid. Now I can see that I have a cut area on this element. Now when I use the exploded view, now you can see that I create a slice. All right, and the more grids I have, the more slices I will have. So let's say if I create a scatter and VDB from polygons, so I want to put my particles inside of this guy and set like, I don't know, maybe 10 points, and then use the point transform. Oh, come on. Sorry, copy 2 points. So here's my, points to copy 2, and here's my grids. Different grids here. And I can make many slices from here. Cut this element like a knife. And let's make the attribute noise. Let me just make it more understandable. So here's my points. And let's add the noise to the normals. Remap it. So now you can see that we create a lot of different planes in different directions. If you look at the cut polygons, it's create like a noisy thing here, and we create a nice result. Many fragments. And of course, if I want to, I can add the mountain top to the grid, and that's how we can create nice interior details. Maybe I need to increase the detail of this plane, so 100 to 100 because it's pretty big. Guess it. Yeah, it works fine. And yeah, we need to make a deal with the normals and all this stuff, but anyway, you can see that this thing works. So flat wire shader. So we can control the detail of the inside area using the grid. In this case, in the mountain top, the amount of polygons. So the Boolean is a pretty interesting method because we also can create a primitive groups like A inside B, B inside A to have an ability to separate those primitives and polygons depending on the position. If they inside of geometry or outside of geometry, we can apply different textures. We can use them for generating particles for, I don't know, for debris, for the smoke trails and other stuff. So this method is very good, but the main problem with the Boolean that is very slow. If in this case we're creating just a bunch of fragments and it doesn't, we don't spend a lot of time. But if we have a complicated geometry, it's take a while, and sometimes we have some bad results. I'm gonna cover this a little bit later. So the another one case is using the Voronoi. So the same stuff. Let me copy this. I'm gonna use the same geometry. I'm sorry. Like over there. So I have a scatter, and if I type Voronoi fracture, we will simply see that we use those points for creating fragments, and it's working really fast. If I type here 100 except of 10, you can see that just we pass a few seconds and we have a result for this. So we have a nice fracturing. But how the Boolean works, in fact, let me make it new. So if we have the point cloud, all what it does is creating the connections between those points, find the middle, and create some kind of a cells between those points. In my case, they almost in the same positions. So here, 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 and find this, create some kind of, it's looking like a brick in this case, but I hope you understand the idea. So each time, if we create 100 points, it means that it creates some kind of 100 fragments, because it simply creates tells between the points. So in this case, if we go here to the scatter, well, actually, we can dive inside of the Voronoi fracture, can allow editing of content and look inside how it works. It's always a very good idea if you want to know how it works with any tools, and if it's the HDA, and we can dive inside of this node, we can look that it contains from the simpler nodes here. So what we have is actually our particles here somewhere, outside group does need. So this is an input geo, and this is our triangulate points. So actually this is our points from the scatter, and then we triangulate them. We create connections, that's those red ones. And then we have the cut each piece. So we use those connections to define the middle of this and create those some kind of clusters or cells, I don't know. And we use those cells for getting fragments. Also, if you want to, we can create some attributes. If you want to set the interior normals, create interior group, create exterior group is by default created here. And even building constraints, if you want to do this, is the second input from Voronoi is our constraints. So if we look at them, it's constraints. We talk about constraints, how they work a little bit later, so let's just keep in mind that we can do this. All right, so again, we have interior group by default, outside and inside. So each time if you want to, we can use the blast node and say that, okay, let me just leave the outside group. So this is like polygons created by Voronoi inside of the geometry. And this is our outside group. Okay, the geometry we had till fragmentation, so we can separately use them for something. So the main advantage of the Boolean is the quality of the fragments, and the main advantage of the Voronoi is the speed. So we create less errors because it's very fast, it's very simple, even with the complicated geometry. But we have a very flat surfaces here. So the main problem with the Voronoi is that we create just one primitive per one point. So if we have like this point and we have 4 neighbors for this point, we're gonna have a piece with 4 edges. Well, in fact, in 3D, it's gonna be like 6 or more neighbors, and you can see that this fragment is very, very simple. There is no noise inside of this fragment. And it can be good in some situations when we have a low size fragments and we can't see the details inside, or we can add some kind of texture with displacement on this. But mainly if we create the distractions, kind of, I don't know, the ground, the rock, concrete, something like that, we need to have a noise inside to make this more realistic, because if you look at these fragments, we can't see such kind of fragments in the movie because it's looking very weird, you know, like back in 19s or no, 18s, 80s, back in 80s. All right, so what method we will use with the ship? And here's another one thing we can work with in the new versions of Houdini is the thing called RBD, material fraction. And this is a very powerful node because there was different versions of Voronoi, there are different versions of Boolean in the previous versions of Houdini. At some level, Voronoi can create even inside details, create some kind of a noise on inside edges, but they remove the stuff. And now we can see that on the stage we have a nice node, the RBD material fraction, and it's really powerful node. When I saw this node for the first time, I said, oh my god, I think that all our questions just disappear, because now except what I want to use, the Boolean or this or this or this, now we can use just one node and define what fragments I want to have. So let's add another one, explode view. I just want to show you the result of this RBD. So there is always, by default, we have even scattered inside of this node. So we don't need to use the scatter it if we don't want. We can simply go here and say, okay, I want to have a 5 points for the concrete fracture 1, and we have the second level with 5 points. So what does it mean? It means that we create 5 elements in the first level. So we can see that now we cut this element into some different fractions, and then if you want to use the next level, we take each of these pieces and make the cutting again. So we break those elements in the second level. So we have a different concrete fractures ID, and if you go to geometry spreadsheet, go to the name, we also have a proper name for this. So we have a 000 or 0. So we have a different name for each point. Now we can understand from what level this fragment. So it's really powerful tool, but not, you can see that it's looking like a Voronoi at this stage. Yes, like we did it here. We have the same speed, so pretty big speed, and we have a flat surface over there. But the really nice thing here that we have the volume, we have the fog volume here in the setting. It means that our points represented not like in the scatter by default. We can use the volume inside of this node and separate those or place those points non-irregular. So in some area we'll have more points, in some area less points. Therefore we will have more random result for the fragment size. It can be tricky and interesting. In fact, we can do this manually here. You can take our volume and create like a density inside of this volume, apply the noise to this density, and say that let's use this density to create a scatter, scatter for our points, and in some areas points will be more, in some areas points will be less, so on and so forth. So now we can do this in one node. And if you want to, we can use the input points. So if I said, okay, I want to find the places for my fragments, so I can connect my last input from the RBD material fracture to the scatter node, and we should have almost the same scattering. Just stop it because I want to remove the second level. I don't need to create any kind of levels, just one level, and that's it. Let's go back to frame 1 and just to update this. And it should create the same result. If you go to exploded view, you can see that it's, well, almost the same. Just tiny bit of difference, but it's not looking way different. Okay. But what is more important here that we have details. We have a chipping, which is also a nice thing, but we have a detail. I don't want to, to cover all those parameters for RBD material fracture because we won't use it. I just want to explain why a little bit later, but this tool is very powerful, and I use the RBD material fracture when I work with, with a building, with a ground or something like that. But when we talk about complicated geometry like vehicles, it can be a ship, a huge starship with a lot of details. The RBD material fracture sometimes create not the best result, and I will show you why. And the problems can became when we use these things inside of the detail tab. And when I apply the edge detail, it takes some time for calculation, but it's create a very interesting thing. It's create the noise inside of each of those inside polygons. So our fragments now is like a combination between Voronoi and Boolean, because we have the same fragments like from Voronoi fracture, but with the edge details like from the Boolean. So the speed and quality from the Boolean and the fracturing from Voronoi. Come on. So you can see that it's a very simple object. It's not too many points, just 100 points, and it's take a long for calculation. So let's imagine if we have a big object and a big amount of fragments, it can take a lot of time. So let's say I test this method for my ship, and if I put all my geometry except the others, so except of the small objects, I take just the main big elements, and when I take those elements inside of the RBD material fraction and enable the edge details, there is not enough 32 gigs RAM to calculate this. Yeah, it's just Houdini just fall down and say, hey, what do you want from me? Okay, I like make pause because it can take a long time. And Houdini just fell down, so I restore back that what we did. And by the way, I forget to enable the FocBDB here density, so my points was created just on the surface. So I changed the density, so now all my points are inside of this rubber toy. So what our interior detail doing for us is adding, let's go to flat wire shading, and is adding the details inside of the fragments. So it doesn't take too long here for now because we have a pretty simple geometry, but what is the main problem in this situation, that how this thing works? Now it's like a combination of Voronoi and the Boolean. So if I say the new, so the Voronoi creates some kind of the cells. So it creates cells, I'm sorry, like this, that. So this like a fracturing we create here. So inside of each of this cell we have a point. So that's a point is like a cell. And later we take those cells and we apply the noise to them on the surface, like here, and etc, etc. And what is the main problem with this method is, let's imagine that we have a big object. This can be our part of the ship. And when it created cells, it's very important that all those primitives should exist inside of the object and go outside of the object. So it should cover all object volume. To do this, RBD material structure, create the bounding box and try to match with the size of the object. But sometimes if we have like this cutter object is not going outside from the original object, it can't create the fragment. So we can have an error in this area. So this fragment can be good, this good, this good, but this fragment can be bad because we are creating the cut surface till the end of the object. So to make sure how works RBD material structure, let's go inside of this. Let me allow editing of content. And basically I don't need to create any constraints. I don't want to do this. By the way, it can create a constraint. So it's a very powerful node. It can create a detail, constraints, even different types of constraints. We have many settings here, but if we go inside of this node, when we won't go to more here. So we have the constraint setup. We use the RBD constraint properties for set the proper constraint setup here, depending of a different type of constraints. You can see the applied constraint 1, 2, 3, so different properties if we select depending of some options. So there is update constraints, but the main thing is here. We have the fracture, concrete fracture, glass fracture, wood fracture. So yeah, inside of RBD material fracture, we can select the material type. It can be glass, wood, or custom type. For many things, we will work with concrete, even with the metal, but for the glass, it's very specific fracturing, and the wood is very specific fracturing, so we can select them. In our case, we're going to use the concrete. And if you go inside of concrete, you can see the RBD concrete fracture. So it's a different nodes here. You can see that they have a separate properties depending on the type of the fracturing. Inside of concrete fracture, let's go inside of the SLO editing of content. We can see that again, there's a lot of different nodes. So it's very heavy structures. That's why it's using some type for creating fragments. So there is again a lot of different objects. There's the chipping, that's the primary scatter callback, that the guide geometry, the fracturing itself, and fracturing itself is used the RBD recursive fracture. Again, there is another one node. If you dive inside, we can see the fracturing, how this works, the recursive fracturing. So we take the proxy geometry, we take the original geometry, so we pack it, and then for each loop, we create the different, we create a fracturing using, ta-da, the Voronoi fracture node. So again, depending on many cases, you can see different options here because again, it can be, there is a different input material. There is a sketchy callback and there is another Voronoi fracture depending, this is the fracture 1 and this is fracture 1. And depending on the input information, we can select between them. All right, so if we select just a simple fragmentation, we can see that originally we use the Voronoi fracture node. Okay, then we pack, then we updating constraints, rewire constraints, and pack again. But what is most interesting is if you go back here in the fracture, we have a detail. So there's two options actually. It's a detail and the H detail. If you look at the RBD material, we can see there's, yes, I need to save this file because if it's will fall down again. All right, so we have a H detail, which is basically create like a noise pattern in all those and inside polygons and in the cutter area. If we apply just interior detail, it will have the H quality is the same. You can see the straight lines here, but it will add the noise inside of the polygons. So the H will be the same, the straight, but the inside area will apply the noise. So that is the main difference between the H detail and the interior detail. So the H detail is back to concrete fracture. The H detail we can use manually. We can use the RBT interior detail node. It's a very interesting node which can just take our inside group. You remember that our Voronoi by default create two groups, inside and outside. So we take our inside polygons and apply the noise for them. Okay, but the H detail is a little bit complicated stuff because it's all about here on CSG Voronoi node. It's a subnetwork. And if you dive in, there's a lot of information, so you can see we can spend an hours to find how this works. So now we can see this is our cells. So basically, this what I paint here. This is our cells, and this is our build cutter geo. And now we're gonna use we're going to use the Boolean fracture. So basically, we take our cells from the Voronoi. You can see the Voronoi cell point. So that's actually what Voronoi creates for creating the nice fracturing. And we take this cutter geo, make some resampling for the primitives, and then the smoothing to add more quality, to add more polygons here, and the fracture noise. So basically, this is our cutter geometry for the Boolean. This is our cell. So you can see that we applied the noise over here on our Voronoi cells. I call the cells, I don't know how this is called in cell, yeah, cells, okay. And then we create a Boolean operation. There is also some different Boolean operation. You can see Boolean fracture. So it's not a Boolean, it's Boolean fracture. If you dive inside, so as the next level, we can I I see that it's never stop. You just go dive and dive inside of this, and we can see here that it's looking like our Voronoi fracture is actually that's our Boolean fracture. So inside of this we have a Boolean shutter. So this is our final operation. Okay, so that's how it works, and there is very interesting text here. So it's clean geometry for recursive fracturing. Switch to Voronoi fracture when Boolean fails. So what does it mean? It means that if we have the bad result, if Boolean fails, if it creates some kind of this thing, we will switch to Voronoi, which is never happened. So in Voronoi fracture, there is no improper fragments because they always create proper cells. Okay, and so how we can switch between if Boolean fails, how we can switch to Voronoi and say, okay, if this fragment is bad, let's just make a simple fragmentation, maybe without H detail, or let's separate this fragment from the RBD material fracture, and maybe I will do a different fracture type. Maybe manually I use the Boolean or something like that. So all fragments which is good, we will keep, we will leave as they are. But if we have a bad fracturing, let's separate this bad fragment and let's make some, I don't know, some work with those. So how we can do this? And we have a situation. Let me just find my scene. And here we go. This is my scene I created for this training. So it's like a test. That's my destruction version 003. So in this stage, I tried to use the RBD material fracture. So I use the input points and use just a part of the ship to make it more faster. So at this stage, you can see that some areas have fracturing, nice fracturing here. We have the edges. So as you can see, I applied the H detail for fracturing, but some areas is not. So you can see we still have some, slicer planes, the cutter elements, and it doesn't work. So some fragments are fine, some not too good. So how we can fix this? How we can find which fragments are bad and we can do something with those fragments? Maybe change geometry, fix topology or something like that. Let's go inside of this. Oops, sorry. Let's go inside of the RBD material fracture again. Let's go here to concrete because we use a concrete fracture, and or even not here. No. Oh yes, here, but okay. It's doing something. Again, maybe I try to stop it because I don't want to wait too much time. It will do fracture again. I don't want to do this. I just need to set to manual update because it will create a fracture each time, and I have to spend like 10 minutes to do this. As I said, it's very, very slow. If we have a complicated geometry, it took too much time for creating fragments. And this is just a small part of the ship without too many details, and it's still too slow. Again, I need to make a pause. Okay, so while this thing is calculating, I just want to speak about the possibility of going inside of each node and find the way to work inside of this. So how this works? Why is important? Many people, some people who I know work in Houdini for the many years, and they even don't have any idea what's wrong, what is going on inside of the RBD material fracture, inside of the Pyro solver. It's not interesting. They know how this works. They know that we have those properties, and that's enough. I don't care about what is inside, but it's really, really very useful to understand how works this. It's not, you don't need to go to each of those nodes and look how this works and what they're doing, because it's really you spend a lot of time. But sometimes there is very useful information, many useful information. The same with those Voronoi. There is a nice possibility how we can stick small pieces back to the larger ones. So how we can find the closest attached pieces. There is a lot of different information you can find very useful for your work. And it's really, really, really interesting because the few years ago I began to learn the HDA. I begin with the volumetric. I go inside of the Pyro solver. I teach the math. I teach the formulas, how the volumetrics works. What is an advection? There is different types of advection. There is different types of projection. Why we need to apply projection. And there is a lot of, I use this information in my Houdini FX training, and there is a lot of formulas, there is a lot of arithmetic stuff where we try to find out how this volumetric works. And when you understand how this works in a low level, your work in Houdini became much easier. It's really much easier. You know, it's like a car. If you know how to drive a car, you can use this knowledge all your entire life, and even if you don't know what is inside of this engine or how your gearbox work, it doesn't matter. You know how to drive, you know how those button works, you know how you can open the doors, you can change the wheel if you want to, you know all the stuff. And I'm not interested in more. I can drive the car. That's all what I want. So the same, but if you want to make an adjustment, if you want to make your car more powerful, you can't do this if you don't have a proper knowledge. You need to give this car for someone who know how to do this. And the same thing in Houdini. You can work in Houdini even without knowledge how those thing works in a low level, and that's fine. It will be enough. But if you want to create something, if you want to adjust this work, if you want to create something new, you really need to know the more advanced stuff. And yeah, again, many people say, there is no advanced tutorial in the internet just for beginners. I really want to know how this works. So there is a lot of interesting things inside of Houdini. Just go inside of HDA and look how this works. There is a lot of VEX coding, interesting VEX coding. There is a lot of interesting methods how we can adjust your fracturing. So basically it's the same Boolean, it's the same Voronoi, but now we can see how many different possibilities we can, polydoctors, very fine thing to fix geometry. So you can really find the proper ways to fix something, to change something and make something more useful. Like over here, what I want to show you is I guess inside of the Boolean fracture, or where, I forget about that. Just go here or not. Yeah, clean geometry when Boolean fails. So with the switch, select input detail, not here. It's not that. What I want to find, I need to find my two Booleans. And they should be somewhere here. Let me back here, maybe it's somewhere there. Just want to find where this. Yeah, I switched back to this, to my ship. Okay. It's disappeared again. Oh, here we go. I don't know why it doesn't go to flat white shaded. Anyway, so inside of concrete material fracture, inside of CSG Voronoi, there is very interesting thing. And not here. Oh, here we go. In this CGS Voronoi. There is a very interesting thing. We have a two Boolean fracture and we have a switch clean. Again, switch to Voronoi fracture when Boolean fails. So how we can understand where Boolean fails? We have a node called compare B box size, and comparing the B box size and the length. And if it's different, it's great. It's switching between this. And what is interesting, there is an interesting attribute. It's called broken. If the ratio less than 0.999 is changed less than 1. So the broken attribute actually can help us to understand which fragment will be broken. So in this stage, if we go to geometry spreadsheet and we update the stuff over here, we have this broken attribute into primitive. So that's 0 for now. And if we go outside of the node here, geometry spreadsheet, and update this stuff, there is no broken attribute because it will be removed inside of the RBD material structure. So to have an ability for importing this attribute outside of the RBD material structure to understand what pieces we need to fix, I want to disable the node. We should delete this attribute again. I cancel cooking because I don't need to have this fracture again. And you can see that there is no our attribute. Let's find where this attribute goes. I guess it should be somewhere. Not here. I guess inside of the primary. Primary. Allow editing of content. And here, yes, attribute delete broken. So this node is delete our broken attribute. Let's let's disable this node and again update it. So now we should have this broken attribute here, and we can find what we want to keep and what we can remove. And here we have the broken attribute. And let's make blast node. Connect to fragments, and let's select the let's choose the primitives, and it's my with double to broken if would equal to 0. Let's look at that. Let's update. So we have just one. Where is this? I can see it. Go to auto update because okay, so this is the proper fragments, so without any kind of problems. And if we uncheck this, so now we can see fragments with the problems. So you can see that there is more problematic fragments than corrected. So anyway, to fix this problem, we can take a name of those fragments and try to fix them. But with the different methods, we have a nice, like a polydoctor node. It's a powerful node. There is a lot of different possibilities to correct topology, to work with edge points, primitives. But honestly, I don't know what is mostly those parameters doing because I'm not working with modeling. So we can just try to fix something. So we can fix the small edges. We can work with non-convex. We can work with thickness. So there is a lot of different options. We can fix our geometry. And I try to do this with my ship. Honestly, I try to work with RBD material structure because I try to create some kind of a new type of fragmentation. But even with this thing, I fix some problems. For some element, there was problem with the small edges, with some elements was problem with the I don't remember, maybe it was sickness or something like that. So I spent like a half of a day to fix all those issues, but when I do the same for all other part of the ship, again we have a problems with fragmentations, and even my poly doctor can't fix this. So what type of fragmentation we're gonna use in our case? What we're gonna use in our scene where you are. So again, it's very, you can see the poly doctor also here. You can see the topology, connects many of polygons. So there is already some fixing inside of the RBD material fraction. Again, it's very interesting to look at this. So if you have a time and if you want to look inside of the RBD material fraction, you can find the proper way to fix something, or just to understand how this fragmentation works, and you can do this manually. So if something doesn't work inside of this node, you can do this manually to look in the idea how work RBD material fraction. So what method I want to use? I want to use a Voronoi fraction. It's much faster. It doesn't create an errors, or those errors is, well, not so often like with Boolean. But how we can fix a problem with our the edge details? I don't want to have such a straight lines on my ship because it's metal, and when it's broken, when we break a metal with an explosion, it's creating like non-linear edges. So how we can fix it? As I show you inside of the RBD material fraction, we have a node which can help us to create the interior detail, and this node called RBD interior detail. So if I add this node here for Voronoi fracture, let me just check this thing here, and we connect this floated view, we can see that it is already tried to find the inside group. So now we can see that we have something inside of our geometry, inside of our inside primitives, we can see it. So we can work with an amplitude, make a bigger noise, we can work with the detail size, we can small them down to add more polys. Now it's looking more interesting. You can see the noise, the amplitude, again, maybe bigger, to have a bigger noise than that. But it doesn't fix our edge problems, because from this angle you can see we still have straight lines for our fragments. So inside they're good, but for straight lines it's not a good. And in our case, I even don't care about RBD interior detail because we will create a thin object. It's a metal, it's a list of metal. So in fact, I don't care about interior detail because the slice for the metal should be smooth. So I don't want to create some kind of a noise on this slice, but I don't want to create a slice like this. It's not like part of the metal fragment. I want to create something like, I don't know, like this. So create a nice noise for the edges. So how we can do this? In fact, it's very simple. It's a very simple method to apply the noise for the edges. The first thing I want to do is create a rest position for my points. So if I apply the rest for all points, my geometry, well, what is rest doing? Just try to save the current position for all points. So we can see now that our rest in this frame, our rest is is the same as the position of our points. Now, before I do the Voronoi fracture, I want to apply the noise to our geometry. So you can use the attribute WAP and apply the noise there, or we can use the attribute noise tool. So let's apply the position, and let's go here and look at geometry. So now you can see it's very noisy. Maybe I do the remap. Oops, that's too much. Maybe like minus 0.2. Let's copy this. Copy parameter, pass relative reference. and point to here, copy parameter, paste relative reference over there. So now we can control the amount of noise when apply and the minimum maximum, the element size also, maybe smaller element size, something like this. Okay, so maybe I want to make a remesh and I need a smoothing and 0.02 to make it more accurate. So now after remesh I make rest, then add a noise, then add a fracture. Okay, so I create a fracture for this weird geometry. Okay, that's work and that's how it's looking now. So now the edges are straight, they're linear, but what if I apply the attribute triangle, say that now the current position for my points is from the rest. So I change my point position back. So I store this position in rest, I change position using the attribute noise, make a fragmentation and make all those points back to the current position. So now I can see that my edge details is much better, so there is no line. So maybe it's noise a little bit bigger than I expect. I don't know, something like this, 0.025. And come on. Let me just look at the attribute. 0.025 here. So a little bit of big element size. And I just want to find the proper scale for the noise. And go back to exploded view. So yes, it takes some time because we apply the noise, we work with position, we work with Voronoi fracture, but the small noise, I guess, I need a bigger because it's again linear. Not a big noise for this. So let's minus 0.5 and 0.5. And maybe elements smaller. So they just, we need to spend some time for creating the proper scale for our noise. Okay, so now this much more interesting. So if you don't want to use a rest for some reasons, you can just, I don't know, create any attribute you want. So create a custom attribute. So let's say the vector attribute, I don't know, the old p, so the old position will be equal to current position. Then we do all those manipulations and set that now my position will be from the old one, and it should be the same. So you can apply any attribute for this. And if you want to, what is wrong here? Just should create the old P, the Voronoi, and now it should match. But it doesn't. Why it doesn't work? Yeah, now it's working. Okay. So that's how we can create our fragments with a nice edge detail and do this pretty fast. It's much faster than the RBD material fracture with the edge detail option enabled, and it doesn't have any kind of problems. And we still, if you work with this geometry without thickness, if you want to fill inside, again, RBD, interior detail, that's what we can add here to fix the inside details. So now this looking much better. It looks like we use some kind of a Boolean option, but we know that it's not. Now we applied the noise for our positions. Okay, so we can save it for now, and now we can go and apply this method for our ship. Let's try to find out how we can do this.